down to our very last example for the SDOF vibration response. We have here a mass is supported by a fixed circular A36 steel tube column with a rigid horizontal member estimated to have 4% critical damping. Determine collective stiffness K, angular natural angular frequency, damp angular frequency, damping coefficient, logarithmic decrement, and the damp period T and the K. Okay. So we have actually a figure. So you know that the circular steel tube the base is fixed. So bala sa nato ibutang. The height of this structure is 4 meters. Then it has a mass, no? 3 kilonewton per meter. And then the space here, that is 5 meters. And then we have this steel tube, circular. So we have a circular steel tube with an outside diameter equal to 220 millimeters and an inside diameter equal to 200 millimeters. So yung bato na to ani, we need to find K, di ba? So we have a property for each column. So upat man siya ka column and then we have a property. K is equal to 12 EI over L cube. We have our L, our I is solved pa, and our E is actually determined from this one, A36 steel tube. Ang A36 steel tube, ang E is equal to 200 GPa. So we have 12 times 200 times 10 to the 9 Newton per square meters. I. So the moment of inertia of a circle is equal to pi d4 over 64. Just leave it like this and then over 4 meters cube. So sa nato si I, or I, we have the pi d4 over 64. So we have pi times 2. Ato lang siya yung meter diretso pero din taas. So we have 0.22 meters to the fourth over 64 minus the inner diameter 0.2 to the fourth over 64. So eventually we have an I is equal to 3.645033 times 10 to the negative 5 meters to the fourth. We substitute this value there, we'll arrive that our stiffness is equal to. So finally, we have already our K 1,366,887.329 Newton per meter, or this one in kilonewton per meter, 1,366.887 kilonewton per meter. Next, we got to solve the natural frequency omega. This is equal to K over M. So we have the square root of our K is equal to 1,366,887.229 Newton per meter over the mass. So if you notice, si mass is like this. We have 3 kilonewton per meter and then distributed siya for 5 meters. So, tali lang na siya. You just convert that into Newton. per meter. You have 15,000 newtons, and divided by 10.81 meters per second squared. The omega is equal to 29.899 radians per seconds. Then our C, the damped angular frequency, is equal to omega times square root of 1 minus psi squared. Now we don't know the psi, or do we know? There is a 4% critical damping. The damping is 4% of the critical damping. So damping ratio is equal to the damping over the critical damping 2m omega. So following this, our C is equal to, or our psi is equal to C over 2m omega sa psi 2m omega. Or 0.04 of 2m omega. Actually, this one, the 4%, mo na ni siya itong damping ratio. So, our damp angular frequency is just equal to 29.899 square root of 1 minus 0.04 squared. And then we have our damping coefficient, rather the damping angular frequency, 29.875. So, doon lang kayo, no? Radians per seconds. The damping coefficient C, that is just the 4% of the critical damp. This is equal to 3,657.37 kilograms per seconds. Our here has to find the logarithmic decrement. Since wala man tayo U1 or U2, etc. Now, you have the 2 pi psi omega over omega d, or 2 pi times the psi, that is equal to 0.04. Times omega over omega d, that is equal to 29.899 over 29.875. Our logarithmic decrement is equal to 0.2515. And then the period t, that is just equal to 2 pi over, the damping period is the 2 pi over omega d, or 2 pi over 29.875 radians per seconds, or 0.21 seconds. This is the damping delay, or the damping period.